Hi everyone, thanks for joining us on this talk about latest scalability improvements that have been happening with Kubernetes. I'm Shyam, I'm one of the developers on the Kubernetes project. I've been working on Kubernetes for a little more than 2.5 years, and I'm one of the chairs for SIG Scalability.
And I'm Yassine Tijani. I'm a member of technical staff at VMware. I've been working on Kubernetes for more than 2 years now.
All right, so let's start with a little bit of background. So Kubernetes started scaling to large clusters a while ago, and this was around 2 years ago. I think it was in KubeCon Berlin, where we made a big announcement that Kubernetes scales to 5,000 nodes. And this got a lot of people excited, and indeed that is the way it should be. And consequently, a lot of people started trying out bigger clusters in their production environment, and they were trying out different configurations and different features. And soon these exposed some bottlenecks that we did not know before. Over time, some particular usages showed us that some of the limits we are hitting in the system, and we started looking into those bottlenecks. And the important thing is we realized that we need to move to a new definition of scalability. Until that point, we were mostly looking at scalability as mainly about the size of the cluster or the number of nodes in the cluster, but scalability is really much broader than that, because there are so many dimensions. As you can see on that picture, there are so many dimensions that Kubernetes has, and you can stress along each of those. So you have number of nodes, you have number of pods, you have pod churn, pod density, number of services, and a lot of these things. So scalability is really a multidimensional problem, and we realized that with the bottlenecks that we came to know from a lot of users, we realized that there are some improvements that we need to make in different areas. And we ended up improving a lot of these. So I'll go ahead and we'll go ahead and look at some of these new and exciting improvements that have happened in the last few months. So the first one is about having too many node revisions. In Kubernetes, kubelets post periodic heartbeats to the control plane to tell the control plane that the node is still alive. So this is done every 10 seconds. So this means that the kubelet posts a new version of the node object once every 10 seconds. And each of these objects, each of this revision that is posted is stored as one revision on etcd. And if your node object is really big, probably because there are too many images that have been pulled onto the node, or there are a lot of volumes that have been attached to the node, which can make the node object really big, like 10 KB or even more, then that multiplied with this factor that there are so many revisions of the object can eat up a lot of space. And even worse, when there is a really big cluster, like let's say 5,000 nodes, this gets multiplied by a factor of 5,000, which means your etcd pretty much ends up being filled with just node objects. And we've actually seen this happen to some really big users of Kubernetes. And once etcd fills up, your cluster is pretty much frozen with respect to writes, because etcd can't take any more write requests. It enters a read-only mode. Because of this problem, there are a few dimensions that suffer. It's mainly the number of nodes and also the number of images or volumes that you can have per node. So how did we solve this problem? We started out with a simple idea of splitting away heartbeats from the node objects, because conceptually, heartbeats is something different from the specification of the node, like the spec and the status of the node. So we introduced a new API called the Lease API for representing these heartbeats. And because now we've separated heartbeats from the node objects, we are able to independently update both. We don't have to tie together like updates of node status and these heartbeats. This is a tricky thing to make work because there are many small caveats that we had to think about and making this backward compatible with old clients and things like that. So the goal of doing this is that once we separate heartbeats from the node objects, these heartbeat objects are really small, so even if you have many revisions of this, it's going to be okay. And the node object now can only, Kubelet can only make updates to the node object when there's actually a meaningful change in the status, in the node status. So we'll go ahead and look at this new API, but just a little small note on the feature availability. This is in alpha in 1.13, and in 1.14 this is in beta, the node heartbeats. And it is also turned on by default. So if you're running a 1.14 cluster, expect to find these heartbeat objects in your cluster. So let me quickly go through this new API. I won't go into too much details, but the object on the left is the node heartbeat. The blue fields represents basically whatever the things that you should be focusing on. It's a pretty small object. It holds a few things like what is the name of the holder of this lease, which is the name of the node itself, and how long the lease is valid for, and what time it was last renewed. So Kubelet is now responsible for periodically updating this object. And the node status now no longer has to publish these new heartbeat timestamps, so we basically isolated both problems. All right, the next problem is with Kubelet periodically polling for secrets and config maps. So for all the pods that Kubelet runs, it has to get the secrets and config maps that those pods reference. The way it was doing it up until a while ago was periodically polling for them from the API server by making GET requests for each of these individual secrets and config maps. And this ended up being really expensive from the API server perspective, especially when there's a really big cluster where there are so many nodes and each node needs a lot of secrets and config maps, because that eats away a significant chunk of the API server's request queue, starving it from other useful requests. So there were some short-term stopgaps to kind of mitigate this issue to some extent. We introduced caching on the client side for these secrets and config maps, and we reduced the poll frequency for larger clusters to reduce the effect of these large number of calls. But they're not really solving the problem from the root, and they're more like just band-aids to the problem. So because of this, the dimensions that suffer are mainly the number of nodes and the number of secrets and config maps that are needed by your nodes. We solve this again with something that seems like a simple idea, which is to watch for these secrets instead of poll for these secrets periodically, and watching is much lighter from the control plane perspective. So yeah. The feature availability for this is a little bit tricky because we actually enabled this kubelet watching, secret watching in release 1.12, but we later realized that there was a tricky bug with Golang that caused some issues when there are some nodes which have too many secrets or config maps. I'll briefly explain what that issue is, but basically what you need to know is this feature is not currently usable in 1.12 and 1.13 releases, but it has been enabled in 1.14.2 patch release, and that patch release actually has the Golang bug fix as well. So you can safely use this feature and get the performance benefit of watching. So the bug itself is that Golang 1.10 and 1.11 made a breaking change with the HTTP client library that when all the streams of your TCP connection are exhausted, the client does not automatically start a new TCP connection. And in Kubernetes, we multiplex watches onto a single TCP connection, and each watch uses one stream. So as soon as there are 250 secrets or config maps, you have 250 watches, and that eats away your TCP connection, and the node can then go dead. This behavior was fixed in Go 1.12, so we went ahead and fixed that for release 1.14. All right, so IP tables performance. Raise your hands if any of you have ever had any issue with performance of IP tables. Okay, that's quite some bunch. All right, so IP tables is used by Kubernetes to program the networking layer on the nodes for service routing and load balancing within the cluster. And IP tables has been around for a long time with the Linux kernel, which of course comes with its own advantages, that it's a really mature tool and it doesn't have many bugs and it is quite feature rich. But as come with the advantages, there are also some disadvantages of legacy systems in that it was not very well written with respect to performance. The main problem is that IP table stores the rules in the chain as a linear list. So this means that whenever you have a large number of services, and so each service is represented as one rule in this IP tables chain. So when there are a large number of services, this chain becomes really big, and this affects both your IP tables data plane operations and control plane operations. So data plane operations is basically routing of the packets, which is done by evaluating those rules. And because it's a linear list, you have to go through the whole list, so it can be really slow to route the packets. And the control plane operations are changing these rules themselves, which is updating IP tables. And IP tables doesn't allow you to incrementally add new rules. So what you need to do is you need to get the current chain and add a new rule and just post this whole thing, which can take up to a really long time, and it can take up to 30 seconds if you have many services, of the order of thousands of services. So because of this, some of the dimensions that suffer are the number of services and the size of services, like how many pods you can have in a service. So how did we solve this? IPVS. So I'm slightly hesitant to call this a solution just yet, partly because the community is still on its way to decide and make up its mind on if this is actually the route we want to take down the lane, if this is the long-term path we want to choose. And also because IPVS, even though it has reached GA in 1.11, it's something that is still kind of considered in experimental mode, because not many providers have yet started supporting it in production. And also it's a relatively newer thing as compared to IP tables, so it's still going through the bug stabilization phase. All right, so what is IPVS? IPVS is an alternative to IP tables, especially for the service load balancing part. It's mainly written keeping load balancing part in mind. So it also holds rules for packet routing, but it stores them in a different way as compared to IP tables. It uses better data structures, it uses hash tables, and hash tables are much more efficient as compared to linear lists. So basically that allows for much more efficient operations with the data plane and control plane operations that I was talking about earlier, and it gives really high scale with respect to services. It's still missing some functionality, and there's still a way for it to mature, but this is one really good option for us right now. All right.
So one of the issues that we encountered is also scheduling performance. Some workload really needs some high scheduling performance, and on large clusters, scheduling throughput is usually around 90 pods per second on a 2,000 cluster, and 30 pods per second on a 5,000 node cluster. When we use the affinity feature, it drops down to 5 pods per minute on a 5,000 cluster. So here the dimensions that are suffering are pod churn and the number of nodes. Thank you. So how did we solve this? First of all, one of the optimizations that we've done is we score only a subset of nodes, meaning that we have the nodes of our cluster, we start filtering the nodes using predicates, and once we found a subset of nodes, we start only scoring priority function only against this subset. So it makes it cheaper. Also, we improved the affinity computing by splitting it in two phases. First one is that we find all the pods that are matching the affinity term, and then on all the subset of pods that are matching the affinity terms, we start filtering by topology key. So this actually also makes it cheaper. And for the pod scheduling latency, by profiling the scheduler, we found that on one scheduling cycle, the scheduler spends most of its time snapshotting the scheduler's cache. So it can get a consistent view of the cluster state. So one of the optimizations that we've done is we changed the data structure of the scheduler's cache to make the snapshotting even faster. As for feature availability, the scoring and the affinity are available since 1.12, and the cache snapshotting is available since 1.14. Okay, so another issue also is the way we handle events in Kubernetes. We've encountered multiple scalability issues with events. Either they fill the etcd database, or they also overloading the API server by making requests, by clients making requests to create events. Also, we had a very poor user experience to query events and use tools such as monitoring, tracing, and automation to use these events. And there are some dimensions that we wanted to improve, which are the number of the API calls, the number of nodes that are, for example, emitting events, and pod churn. The way we solve this is basically we introduced a new events API, and with this new events API, we introduced a new deduplication logic. This logic introduces a concept which is called isomorphic events. Two events are isomorphic if they have the same subset of fields. For example, the reporting controller, the reporting instance, the type of the event, the action that was taken, and so on. We also try to avoid aggregation by creating a new event object on top of all the events that we've created to say, hey, I just aggregated all the events. This feature is available in beta on 1.15. So let's take an example here. We have a node, we schedule a node on it, and we try to pull an image. The image is not found, so we're on an image pullback off. The kubelet will try to create an event, write it to client-side cache, and then create it on the API server. When we will try to back off and try to repull the image, we're gonna check if the event is isomorphic, and if it's the same event, we're gonna start what we call an event series, which is basically we increment a count on the object of the event. We write it to the client-side cache, and then we patch the API server to increment the count. And whenever we try to back off, we check if this is an isomorphic event. If it is, we write it to the client cache, but we do not make extra calls to the API server. And when we detect that the series has ended and we do not see any event series anymore, we write what we have on the client cache to the API server to reflect the latest count. Also, we have on the background something that pulls the cache and make a bulk to the API server to refresh TTL keys, because the events are entries on etcd that have TTL keys and we do not want to lose them. Another issue also is related to watch cache. it's watch restart cost. The issue here is that whenever we restart the watch connection, it overloads the API server. For example, let's say we want to watch for a number of pods that has a specific label, and for example 10 pods are matching of 100, and these 10 pods are not changing, but the other pods are a lot changing. So this list gonna have what we call a resource version to indicate the version of the pod list resource. And since the 10 pods are not changing and the others are changing, the pod list resource version is gonna increment, but we're not gonna get watch connection because the subset of pods that is matched is not changed. So when the connection will time out and we will try to reestablish connection, we're gonna try to reestablish a connection with a resource version that is stale. And this is where we get the famous error called too old resource version. And what this means is that the client needs to do a full release to get the latest resource version to reestablish the watch connection. And the dimension that we want to improve here are the watches, the number of watches, and the number of calls that we make against the API server. So how did we solve this? We introduced a new watch event type, which is called event bookmark. It basically tells the clients the resource version they're at. So when they time out, they establish the connection with the right resource version. This is a feature that needs to be explicitly obtained by the clients, so we don't break the existing clients. So when you establish a watch connection, on one of the options that you can specify is allow watch bookmarks. The initial benchmark shows 40 times improvement and decrease in wasteful event processing. As for the availability of this feature, it's going to be available in 1.15 as an alpha. So let's take an example. We're watching for a subset of resource. So we make the list call to get the list and the resource version. We start watching against the API server with a resource version X and specifying allow watch bookmark to true. Right before the timeout minus 2 seconds, the API server gonna send a watch event, a new watch event type called bookmark that reflects the latest resource version. So when the timeout's gonna happen, the kubelet gonna reestablish the watch with the right resource version against the API server, and thus there is no need to relist against the API server.
All right, so those are pretty much the main performance and scalability improvements that we've made in the last few months and over the course of last 3 to 4 releases. So what are we planning to do next? We are still trying to hear from people and from users, like what are some of the pain points they're having. But some of the things which are in our radar at this point, and there are a few things which we are working on already right now, which are planned for in near term, and there are some things which we are thinking. And let me go through the things that we have here. So we are planning to have a new endpoints API, endpoints v2 API. There's a very good talk on this on Tuesday by Wojtek, which explains the new API. So currently, the endpoints API is not very performant for the way it has been designed, because for a service, you have one single endpoint object which stores a list of all the IPs of the pods that belong to that service. So that means that even if like one pod goes up or comes down, you have to update this object and repost this whole thing, even if all the other IPs didn't change. So this becomes kind of costly as you go to bigger clusters and as you have bigger services, because it's not just about updating these objects, it's also about then publishing these, the newer version of these endpoints to all the nodes, because kube proxies are watching for endpoints. Yeah, so the next one is to allow for a higher pod density. So pod density is the number of pods that are allowed to be run on one node. Currently, it's limited to 110 by default in Kubernetes, and officially we support for like a maximum of 110 pods per node. But because of some of the recent improvements with Docker, Containerd, and even improvements in Kubelet itself, we are now able to go higher. And there are a bunch of folks who are already trying like 200 to 300 pods per node. So we might soon increase this default limit, or at least like go higher for bigger instance types. The next one is about rethinking our current affinity and anti-affinity logic in scheduler, because this has started to hunt us in large clusters, because this has become a bottleneck for our scheduler throughput in large clusters, because the way we are computing affinity and anti-affinity currently, we are considering the state of the whole cluster for evaluating the validity of every single node for the pod, and this becomes very computationally expensive. So yeah, so we're still thinking about ideas of what we can do here to improve this. Maybe there might be some significant changes in the feature itself, something to think through. And the last one we have here is watching for arbitrary fields. This is again something far term, where we're still again thinking about this. We're not yet 100% convinced if we want to do this, but this is about watching for particular fields of an object instead of watching for the whole object. If you look at some of the controllers in Kubernetes, they're taking actions based on just like one or two fields of some object. So pretty much whatever else is in the object is like not being used by it. And currently watch gives you the whole object that you're watching for, which kind of increases the resource footprint of your clients and consequently your controllers, because you have bigger objects to process and more memory allocations to make. Yeah, and I put those 3 dots there because maybe there is something that someone among you have ideas about, and you might want to let us know, because this is a good opportunity. And thank you. Let's go to questions.
So with some of these optimizations in terms of data structures, have you seen memory resident size improvements with the API server?
Sorry.
Like memory, like RAM usage improvements with some of these optimizations. Like it seems like if the API server caches events, then this bookmarks feature should show some memory improvements. Just wondering about that.
Yeah. Do you want to answer, Wojtek?
So basically we are, for those who don't know me, I'm Wojtek. I'm another SIG lead from SIG Scalability. So we are basically not focusing that much on memory. It's not still not one of the things that is what most users are affecting. Though, like with Go 112 that we started using in 114, Go 112 is way better with handling memory. Like the drop that we've seen in our like continuous testing is something like between 2 and 4x. So once you get to this version, you will see significant improvement.
So I had a question about the numbers you showed for before the fixes for pod scheduling on 5,000 node clusters, especially with the anti-affinity feature. So you said something like 5 pods per minute. That sounds like very, very slow. I'm wondering if you could expand a bit on what was happening to cause such a slow processing speed for 5,000 elements in a list. Doesn't sound like that much. So what sort of thing was happening that was, if you can, I don't know, maybe it's too large to explain, but.
So that throughput of 5 pods, less than 5 pods per minute is the throughput when these pods are using anti-affinity feature. So also this is like before some of the improvements were made, but the reason why it was so slow is because the scheduler predicate and priority which actually evaluate which together evaluate the score for the node, the way they are written is not very efficient, because how it works is like, let's say you define a deployment of pods with anti-affinity at the node level. So node is your failure domain. So basically, I see Wojtek, you're smiling. Do you have something to say?
So basically the main problem here is that pod anti-affinity is like symmetric here. So when you are scheduling a pod, we are not only looking into how it affects other pods. Like we are also looking into like whether scheduling our pod will not break any other assumptions of any other pod anti-affinities that are already scheduled in the system. So if you are scheduling a pod that in a cluster that has, let's say, 10,000 pods already running, then we need to check whether my pod and any of those other 10,000 pods aren't breaking the assumption for any of the existing like anti-affinity of anything else. So that's like kind of like more than quadratic or something like that. That is like has significantly changed. Like when I was last looking into the numbers, I think in 1.13 we are somewhere around between 10 and 20 pods per second already with anti-affinity. And there are a couple more things coming in 1.15. So we are getting to at least the same order of magnitude with anti-affinity. And there are like a couple plans to not support anti-affinity on any arbitrary topology also, which I was suggesting for quite a long time. It seems that it's currently getting some traction. So yeah.
So for these numbers, is that just a single scheduler process, or is this multiple schedulers?
So this is you mean like is this across multiple pod schedules, or?
So each kube scheduler has its own cache of all the world, right?
Right. So this is just for like one scheduler.
Okay. So
we're not like parallelizing across schedulers.
Any other question? Okay, thank you.
All right, thanks.